Math 2414, volumes, volume of a sphere. Now in theory, you all know the formula for the volume of a sphere. And in the event that you don't, there it is, 4/3 pi r cubed. But if you ever wondered where these formulas came from, did somebody just magically write it down and say, that looks good? The answer is usually calculus. So we're actually going to derive this formula, showing that the volume of a sphere of radius r is 4/3 pi r cubed. Now how are we going to do that? Well, recall that the only tool that we have at our disposal so far is if the cross-section area is a of x, then the volume, which we'll just call capital V, is the integral of that, which kind of makes sense. You may not have thought of this, but when you differentiate, you knock things down a dimension, and when you integrate, you bring them up a dimension. So when we integrate area, a two-dimensional measurement, it takes it up a dimension to volume, a three-dimensional measurement, which makes sense because this dx represents the third dimension. Well, this represents the first two since it's an area. All right, so how are we going to do this? Well, if we're going to do this, we need to set up a solid, conveniently oriented relative to the xy axis so that it is easy to calculate the area of a cross section. So let's start by setting up an xy axis. And where would be the most convenient place to put this sphere? Intuitively, with the center at the origin. Let's draw a sphere of radius r, so we know that this is r and this is r. And to give it a little bit of depth, I'll draw this coming out and one going behind. Hopefully that gives it some depth. Oh, by the way, this would be negative r back here and down here as well, since the radius is r, distance from the center. All right, if we're going to do this, then we need to come up with a formula that says what the area of the cross-section is if we go up to a certain point on the x-axis and cut this sphere straight down. So let's think about this for a second. You've got a ball. I don't have one with me. Let's say it's made of clay or something solid, so it retains its shape when we cut it in pieces. If I take a sphere and cut it and show you the cross-section, what shape will it be? Should be pretty obvious that that cross-section shape would be a circle. So that means when we cut this sphere, we know that we're going to get a circle. So all we have to do is figure out the area of that circle. Well, the area of the circle is pi r squared. So if we can figure out the radius of that circle, then we're in business. Now, where in this picture would the radius of the circle be? In other words, if I sliced this and held it up to you and said, here's the radius, where would it be located in this picture? Right there. Now, right now, I've already got lowercase r representing the radius of the sphere. So I don't want to use that to represent the radius of the circle. How are we going to find something to represent the radius of the circle? Well, we need to connect what we're looking for. I'm going to put capital R for radius of the circle there. We need to connect what we're looking for to the x-coordinate that we're cutting on this plane. So let's go up to this point here, and let's call it, well, if it's over x and up r, it would be x comma r, x comma capital R. Can we come up with some equation that tells us what that radius is as a function of x? Because I know the area of the circle is going to be pi capital R squared, but I need it to be a function of x, not a function of capital R. So what can we do to relate this radius with this x? This radius with this x? And the answer is complete this right triangle, whose base is x and whose height is capital R. If we only had something to represent the hypotenuse, we could set up the Pythagorean Theorem. Too bad we don't know the distance from this center to this circle out here. Oh, wait a minute, yes we do. This sphere has a radius of lowercase r, which means I know that this hypotenuse is lowercase r, and now I can use the Pythagorean theorem to my advantage. The Pythagorean theorem on that triangle would say x squared plus capital R squared equals lowercase r squared. And remember, what we're trying to do is to figure out what would this radius be as a function of x. So I need to know what capital R equals. Well, if I want to know what capital R equals, I can just solve this for capital R. R squared, big R squared equals little r squared minus x squared. And if we square root both sides, we'll get big R equals the square root of r squared minus x squared. Okay, well that's convenient. I now know how big this radius is if you tell me where to cut it on the x-axis. So now I can take this expression for capital R and substitute it into my formula for the area of the cross-section. It's instead of pi times capital R squared, it's going to be pi times the square root of little r squared minus x squared squared. But the square cancels the square root, and we get pi times r squared minus x squared. And now we know the area of this cross section if we cut this solid at this point on the x-axis. Now that we know the area of the cross section, we can set up an integral for the volume. The volume is going to be the integral of the area. So the integral of pi r squared minus x squared dx from the least x value to the greatest x value on the sphere. The least is the leftmost x value, which is negative r. The greatest is the rightmost x value, which is positive r. Now, I know some of you might be panicking because there's another letter in there that's not an x, but it's just a constant, so you treat it as such. Let's integrate this with respect to x. First off, we can pull the pi out, so let's go ahead and do that. Let's do the x squared first because that's the easy part. What's the antiderivative of x squared? 1/3 x cubed. We're going from negative r to r. Here's where you have to be careful though. What is the antiderivative with respect to x of r squared? It's not 1/3 r cubed. Little r, the radius of the sphere, is a constant. It's a number that got squared. And how do you take the antiderivative of a constant? Stick an x on it. The antiderivative of r squared is r squared x. Remember, this is just a number. We just don't know what it equals. All right, it's time to go to town. Let's substitute the upper limit. Pi times r squared r, which is just r cubed, minus 1/3 times r cubed. So we can combine those like terms in a moment. Minus pi times, if we put an negative r here, we get r squared times negative r, which is negative r cubed. Yes. Minus 1/3, and here's where you have to be careful with your signs. We put a negative r for the x, we get negative r cubed, which will have an r cubed, but it will actually be negative. But there's another negative waiting for it, and all four of those negatives together make a positive. Watch your signs. Speaking of which, I think we might want to go ahead and, well, let's go ahead and combine like terms first. 1r cubed minus 1/3 r cubed is 2/3 r cubed. Minus pi times negative 1r cubed plus 1/3 r cubed is negative 2/3 r cubed. Minus minus makes it a plus. We have pi, we have r cubed, and we have 2/3 plus 2/3, which of course is 4/3. Which was what we wanted to show. So, I think it's safe to say that the hardest part about these is the setup, and specifically the hardest part is coming up with the formula for the area of a cross section, because you have to visualize what would this look like if I sliced it, a circle, oh I need to know what this is, but connect what I want to know with what I already know. I know the x, that I cut it, I need to calculate that r in terms of an x, and luckily we can set up a right triangle.